In the last video, I introduced refraction as the bending of a wave, and I'm going to spend a lot more time detail-oriented in what refraction actually is. So let's get started with the definition. Refraction, as I've defined it, is a bending of a wave at a boundary change involving two materials of different optical densities. So if you need a refresher on what optical density is, look at my introduction to refraction videos. So we're basically talking about a medium switch, and this is called a boundary. And my favorite example ever is air and water. So let's say this medium is air and this medium is water, and we have a light wave propagating to this boundary. I talked about at this medium, two things are going to occur. Number one, the velocity is going to decrease. And the reason it's going to decrease is because it is going into a higher optical density. Higher optical density, like I said in the last video, is where you have a bunch more particles bombarding each other, which means light has more opportunity to get absorbed and transmitted. Okay, so the velocity is going to decrease, and also if the velocity decreases, then the wavelength is going to also decrease, right? Because it's related by this formula, V equals lambda times f, which is the frequency. Lambda is the wavelength. So however you see the wave equation, this is the wavelength and this is the velocity. So if this decreases, then this decreases because they are directly proportional. If one goes up, the other goes up, and vice versa. But what I didn't talk about is where this light wave actually goes. Okay, so I said that something happens, it bends, but which direction does it bend? Does it just stay in this direction? Does it bend toward the boundary? Does it bend away from the boundary? What actually happens? Well, you know it's not going to be in the same direction. In fact, it only goes in the same direction when the light wave is hitting it head on. Or in other words, the incident ray is perpendicular to this boundary. We call that boundary, or we call the line perpendicular to it, the normal. In other words, if the incident ray is the exact same thing as the normal, or if it's parallel to the normal, then we say that it's just going to go straight through. Okay, I made a video for geology over seismic waves, and I talk about this a little bit more. If you're hitting it head on, all that's going to happen is the velocity and wavelength are going to decrease. You're not going to have any technical refraction going on. Okay, but we're going to talk about where this light wave actually bends to. And I have a few examples that I want to get through, hopefully practical enough that you can actually understand what's going on, and then I'm just going to give you the properties. So my first example is, let's say that you're driving a golf cart. Okay, let's say you're driving a golf cart in the mud to retrieve a golf ball because you don't want to get your pretty white shoes dirty. I don't know. Okay, so let's say this is mud. Okay, and I'm gonna suck at this, but we're gonna draw your golf cart with wheels as a fantastic golf cart. All right, and it is propagating this way. It's traveling in this direction, straight to the right. Okay, so it's eventually gonna reach over here. Okay, and it's gonna reach eventually over here. But I could have drawn that way better. But eventually, this golf cart is going to hit a place on the mud track like this, where one of the wheels is in the mud and the rest of the wheels are not. What is going to happen? Well, we'll assume that this turf grass is somewhat drivable, and we'll assume the mud is hard to drive in. Okay, so this has a higher optical density, so to speak. If this wheel is stuck in the mud, this wheel is going to move at a faster rate than this wheel. Okay, so what's going to end up happening is, because you can almost think of this like a fixed point, and this wheel is going to travel in this direction and almost rotate it. In fact, it is going to rotate it. Okay, so what's going to happen eventually, since this wheel is stuck and it can't move, and this wheel moves, you're going to have some sort of a bending that's going to rotate in this direction. So it's going to have a direction change. It's going to have a direction change. And let me draw the normal right now. So that's the normal. You can think of this as the direction that the incident ray of a light wave is traveling. Okay, and it is going to bend. It is going to bend in the other direction. It's going to bend towards the normal. Let me show you how. Imagine that was straight for a second. Sorry. All right, so it's coming in at this angle. What's going to happen is it's going to bend in a way such that it's going to drive, we'll we'll say a little closer to the normal. Maybe over here. Right, so it's going to travel over here. And hopefully this is somewhat intuitive. Hopefully you understand that if this wheel's in the mud and these wheels are not, then this is going to turn at a faster rate, so it's going to turn it toward this normal. And I know this picture is kind of bad, so I'm going to simplify it over here in just a minute or so, but just understand that it's going to turn away in a way such that it's closer to the normal. All right, well, let's say this golf cart continues to drive in the mud, and it's eventually going to reach a point where my drawings just get better and better. Let's say that it's at a point where these wheels are still in the mud, but this wheel happens to go out of it. Well, this wheel should be traveling faster because it's the one out of the mud. So what's going to happen is it's going to bend in the other direction. Let me denote that in blue. It's going to turn this way. So what you're going to find is it bent toward this line. Okay, so it went here, it bent a little this way, and then you're going to see that it's actually going to bend in the exact same way. So these are going to end up being parallel. But what I mainly want you to understand is this bending right here. It's bending that way. Right? It's bending that way because it is going from an area of it's bending from a lower optical density to a higher optical density. So it's going to bend towards the line that I drew. Okay, so that was probably a little complicated to understand. I'm not the best drawer, especially on this, so let me just simplify it for you. So we have our little mud boundary. I'm going to draw the normal line, which is perpendicular to the boundary. And we're going to talk about what just happened. But instead of a golf cart, let's say that a light wave is traveling. And I don't know, how did I have it travel? I had it travel pretty badly, but let's say that it's traveling head on, so straight like this. However, it does form some sort of an angle with the normal line. So it's not parallel to the normal. So it is going to bend. Refraction is going to occur. But how? Well, in our little golf cart example, this wheel, you can think of this as kind of a wheel. This wheel reached the new medium first. Okay, so it's going to slow down and everything else is going to kind of bend. Okay, so because everything else is going to bend, you're going to have a light wave that's going to hug the normal. It's going to be a little closer to the normal like that. All right, so just some key notes on that. So we transitioned to a higher optical density. So the turf grass was easier to drive on, less obstacles. It was traveling pretty quickly. So that was a low optical density, low amount of interference, and we're traveling to an area of high interruptions or high optical density. Well, this high optical density is going to account for slower waves, or a slower golf cart, as the example illustrated. Okay, well, these slower waves, or the slower medium, this slower medium ultimately allows for the wave to bend. It's going to bend towards the normal. And I still do this in my head sometimes. I still draw like a little cart thing with one of the wheels in the new boundary, and I kind of think about what would happen if this wheel is in a slower environment with a higher optical density. Then it's going to be slower, and this one's going to turn more. Okay, so it's going to be bent toward the normal. That's how I think about it, and hopefully you will do the same. Okay, so I think that's all on that one. Okay, my next example is a principle that you're not really going to get into too much. It's called Fermat's principle of least time. Fermat's least time principle. So here's the situation. And I'm just going to talk while I'm erasing because it's going to take forever. Let's say that you're a lifeguard, but instead of, being on your little lifeguard post, you're actually in the water taking a little break. But you notice, you notice someone on the beach about to get robbed or something, and you want to save that person. So this isn't working. Come on. All right. I'm just going to keep talking. All right, so the lifeguard is in the water, sees a person on land that's struggling because someone's about to rob him or her. So what do? Well, you probably want to save that person because it's kind of your job. How are you going to get from point A to point B? Okay, this is not working. Hang on. Jesus, okay. Sorry about that. Okay, so imagine this situation. Fermat's principle of least time. I want to get from point A to point B. Now, the situation is that I'm a lifeguard, but instead of being on my post and on active duty, I'm actually taking a break. I'm in the water, but I notice a person on land getting robbed or something. Well, I'm kind of a lifeguard. I'm kind of a good person. I'm going to want to help that person. And in order to get to him or her, I have to take the path of least time. Because, getting robbed doesn't take that long. So I'm going to draw a picture for you. I'm going to draw a picture. Let's say that you have a pool or an ocean with water. I have a person right here. I have a lifeguard. Just pretend that's me for a second. Okay, and the person that I'm trying to save is all the way over here. So I want to devise a path such that it takes the least time to get from my location in the water to the person so I can save him or her. Okay, well, your first instinct might be a little something called displacement. And displacement is just the change in position. In other words, I'm at point A right here. Let's just go to point B. Let's just go from here to here. But you'd be incorrect because you're not considering the different media. All right, this is water. I hope for almost every one of you that it takes longer to swim than to actually run on land. That being said, I want to swim in the water and make that the least amount of time possible, so that the most direct distance from water to shore would actually be this distance right here. That is how I get out of the water most quick. I want to get out of there most quick so I can get to this person and spend the most of my time running, because I'm a fast runner and not a fast swimmer. So the path this person's going to take is right here, shortest distance possible to get out of the water, and then take this path on land. Now, while this plus this is more than this, it takes less time because you have to take into account that water takes more time to swim in than running on land, like I said. All right, so let me illustrate what's happening with a little boundary switch. Let's call this a boundary. And this another boundary. All right, so I am in water. And I'm going to air or ground or just a faster medium. Have my normal. Okay. Let's just illustrate this principle. I am in a slower medium. The last example, I was in a faster medium, and I was going from air to water. Now I'm going from water to air. So I start out in the slow medium, and then where do I go? Where do I go? Well, I go toward this person over here. So I'm going to go away from the normal to get to the person I'm trying to save. Okay, so what I'm actually doing is I am bending away from this normal line. And just to reiterate, this is my normal line. Normal line is always perpendicular to my boundary. All right, so my question is, what's going on over here? Well, here's some notes. In this instance, we are going from a higher optical density, more interruptions, to a lower optical density. A lower optical density. And this is going to account for faster waves. Okay. Also, to add on to that, these faster waves are going to account for bending away from the normal. So let me write that down. if you were going to a faster medium, I just proved with Fermat's principle of least time that we are going to bend away from the normal. Okay, let me write that down. Fermat's principle of least time. If you want to look it up, it's actually really cool. I don't think you're advanced enough to be able to prove some of this, but it's worth checking out. All right. Anyway, okay. So yeah, lower optical density yields faster waves. If you're going to a lower optical density, there's less interruption, so it's going to be quicker. And that faster medium is going to account for bending away from the normal using this little principle. Okay, so just to summarize the two properties we talked about, I'm going to draw two diagrams, and we're going to talk through them. And again, I like the car or the golf cart analogy better, but whatever you remember. I've been doing this for a while, so I just kind of naturally know which is which, but you might not be so quick at first. You'll get there. All right, so we're going to say this is the normal line. That's also the normal line. I'm going to draw this picture a lot. You'll have it on your reference sheet, but I want just to make this clear. All right, so a light wave is traveling to the boundary, and I'm going to make that light wave travel at about the same angle in both cases. Let's say it's a straight ray. All right. Now, the ray that comes out of it is called the refracted ray because there is a change in direction. What's going to happen as I travel from fast to slow? Well, that would be the golf cart analogy. So imagine I have a golf cart kind of traveling over here. It's going to technically reach the slow before. Okay, so it's going to turn in this direction, and it's going to hug or get closer to the normal. So if you are going from fast to slow, you go towards the normal. Let me do this in another color. All right, so if I'm going from a slow to a fast medium, all right, so imagine that the first wheel is in a faster medium, so it's gonna push the car in this direction, whereas these are still slow. So it's gonna kind of turn it in this general direction, and it is going away from the normal, where this line right here is the normal. So if you were going from slow to fast, you're going away from the normal. This concept is extremely important, especially when we get into working with Snell's law. So I wanted to make that very clear before moving on to talking about optical density. Now, in the last video, I defined the index of refraction, and I'm just going to do it again. So the speed of light, c, is approximately, it's slightly less than, but for your purposes, it is 3.00 times 10 to the 8th meters per second. This meters per second is a clue that tells you that we're working with speed of light. Now, this is the speed of light, the optimal speed of light in a vacuum. It cannot travel faster than this that I am aware of. Okay? Now, your actual velocity in whatever medium that you're traveling in is probably going to be less than that. Unless you're traveling in a vacuum, it's going to be less than 3.00 times 10 to the 8 meters per second. So whatever that is going to be your actual, speed of light in a medium. So how quick is light traveling in water or glass or diamond or gallium phosphate or whatever? Okay, so basically all these particles are interrupting it, and it's going to be probably slower than this. I want to talk about what would happen. If I take C over V, I get my index of refraction. That's important. My index of refraction. When is my index of refraction equal to 1? Well, I have a fraction over here. When is a fraction equal to 1? Well, I don't know. 1 is 1 over 1. 6 over 6. Whenever your speed, the speed of light, is equivalent to the velocity. If c equals v, that means your medium is a vacuum. You have to be traveling in a vacuum to be going 3.00 times 10 to the 8 meters per second. That's the only case it is 1. What happens when it is not in a vacuum? Well, when it's not in a vacuum, it's traveling slower. So what I end up having is I have 3.00 times 10 to the 8 meters per second as my c, divided by my velocity. And my velocity is probably going to be slower. It's probably going to be slower than 3.00 times 10 to the 8th. So this is probably going to be a smaller number, less than 3.00 times 10 to the 8th. So what happens whenever I have one number right here and a smaller number right here? That looks like a division symbol. But if I have a number 6 divided by 6, and that's 1, what happens when I have a number less than 6, like 3 or 1.5? Okay, well, I increase. I get a larger number over here. So in any case, in almost every single case, whenever your velocity does not equal the speed of light in a vacuum, your index of refraction is going to be greater than 1. And I also want to make the point that because c and v are both speeds, you're taking a speed divided by a speed. The speed units are going to cancel out, and you're going to get a number. There are no units associated with index of refraction. Velocity, heck yeah, you better have meters per second or miles per hour or kilometers per second or something. But with index of refraction, there's nothing attached. There's no unit to index. All right. So generally, this is going to be greater than 1. Okay. Mostly, you're going to see values that are less than 4 in my experience, but I guess it could be greater than 4. It just depends on the optical density. Okay, so I want to bring these two concepts into light. Into light, into perspective. That was kind of a bad pun. All right, so let's say I have a boundary, and we're going to draw the normal perpendicular. This is a little different than I've been drawing it, but you can see it either way, so I want to show you both ways. And we're going to do the exact same thing that we've done before. So hopefully this should be a review from what I've discussed earlier, and we're adding the index of refraction to this. Okay, so I'm going to have a light wave that is traveling to this boundary. We're going to say that that's straight. All right, so let's say that we're going from glass to air in this first example because I'm sick of water. Don't get me wrong, dihydrogen monoxide, super important, but it is overused. All right, so air to glass in this one. Now, there's more interruption in glass, so this is the slower medium. If I'm going from a slow to a fast medium, can you remember what direction? Is it going towards or away from the normal? Well, if I'm going from slow to fast, I'm going away from the normal. Okay, so what does away from the normal mean? Well, away would be this direction instead of this direction. Well, if I'm going from air to glass, I'm going from a fast medium to a slow medium. If I'm going fast to slow, that's going to be towards the normal. That's the one where it's going to hug the normal. I can draw that so much better. There you go. Now let's talk about the index of refraction. What is the index of refraction going to be in glass compared to air? Well, you know that there's not too many interruptions in air. In fact, it's pretty much 1. It's 1.00 with some numbers. It is slightly greater than 1. Okay, but relative to glass, air has a very low index of refraction. So we say that air is going to have a low value of n. Again, because n equals c over v. Because c is a fixed value, the velocity is going to be really, really close to 3.00 times 10 to the 8th. Okay, it's going to be really close. So it's going to be around 1. So it's going to have a relatively low n. In glass, the speed is going to be far smaller. So I'm just going to spit this out. I don't know if this is right. It's probably wrong. But let's just say glass traveled at 1.5 times 10 to the 8 meters per second. That is at a far slower speed than air. What's 3 over 1.5? It's 2, which is far greater than 1. So this is going to have a high index of refraction because of this slower speed. Now, I want to bring something to light. I said that twice. Never going to get over myself for that. I want to bring this to your attention. So, if there is more difference between the actual velocity and the speed of your light, okay, so I'm going to write this down somewhere. Hang on. If there is a higher discrepancy between the speed of light and your wave traveling, that means your wave is traveling extremely slow. But if there's more difference, between the speed of light and the actual velocity, that means you are going to have a higher index of refraction. Those numbers are different. If the denominator is far less than the numerator, then you're going to have a higher number in general. So this is going to lead to a higher value of n. So in this case, glass has a high n because it has a low speed. Okay, and for this example, just to do it really quickly, air, vice versa, has a low value of n because it's relatively close to the actual speed of light, and glass has a high n. So the last point that I want to make, is optical density. I said that word optical density and you probably forgot it. You probably completely repressed it because it's kind of a complicated term. But here's where it comes into play. Optical density. Well, let's just take a look at optical density just for kicks. Which one of these has the higher optical density? Or in other words, which one of these is going to interrupt light more? Which one's more dense? If you guessed glass, you'd be correct. Glass has a higher optical density. Well, hey, doesn't it have a higher index of refraction? Hey, does that mean they are directly proportional? Yes, it does. Optical density and index of refraction are indeed directly proportional. They're related, meaning the higher my n value, the higher my optical density. Okay, so let's just do it for this one. Air has a low optical density. Light can do almost whatever it wants in air. That means that it's going to have a low index of refraction. Because light can do whatever it wants, it's going to get to its location in the least amount of time. That means it's pretty close to the actual speed of light, which means since the numbers are close together, it's going to have a relatively low index of refraction. So I hope all that made sense. Please rewatch this video as many times as you need. Okay, I know I covered a lot of stuff, but all of it's important, especially the direction of bending. Memorize this, fast to slow, towards normal. There are mnemonics on Google. I'm sure you can Google it, or you can just think of my golf cart analogy, whatever helps you the most. In the next video, I might talk about Snell's law and the actual mathematical relationship between the degree of bending that occurs with light waves in different media. So I hope that video was helpful, and see you in the next one.